Hello and welcome to 9.3, the integral test and the p-series test. These are some tests we'll use to, some actually real tools. I like to think we have a toolbox. We're getting tools. Going down to Sears, getting craft some tools, right? These are the best tools for our toolbox. Hope I didn't violate copyright law by saying that. Anyway, trademark. Anyway, we're getting some tools to be able to find out if a series is convergent or divergent. Okay, so theorem 9.10, the integral test. If f is positive, continuous and decreasing for x being positive, and a sub n equals f sub n, you can make it a function, then the sum n goes from 1 to infinity of a sub n is the integral from 1 to infinity of f of x dx. They either both converge or diverge. So if this integral converges, then this converges. If this integral diverges, then this series sum diverges. So we're going to use the integral test to determine the convergence or divergence of this series. We'll say f of x equals 2 over 3 times x plus 5. And we'll do the integral from 1 to infinity of 2 over 3x plus 5 dx. Now, as we learned, what was it, in 8.8, I believe it was, improper integral, right? So we'll have to say the limit as b goes to infinity, integral from 1 to b of 2 over 3x plus 5 dx. And that's going to be the limit as b goes to infinity of 2 times the natural log of the absolute value of 3x plus 5 over 3, because that coefficient for the x there, from 1 to b. So we're looking at the limit as b goes to infinity of 2/3 times the natural log of 3, absolute value 3b plus 5 minus natural log of 3 times 1 plus 5. So we have 2/3 times, and if I plug in that infinity, it's going to be natural log of the absolute value of 3 times infinity plus 5 minus natural log of 8. That's going to be 2/3 natural log of infinity minus natural log of 8, which is infinity. So this diverges. That's it, diverges. I should say, so series diverges also. Okay, that was example 1. I'm going to need to move that, so again, feel free to pause if you'd like to. Okay, use the integral test to determine the convergence or divergence of the series where k is a positive integer. Okay, so we're going to be saying f of x equals x to the k e to the negative k. No, yeah, that's about right, yeah. So a couple things. F is positive, being that x is 1 or more. F is continuous. F is increasing. No, decreasing, excuse me. Because of this E. How do we know that? Well, if you do f prime of x, you're going to have x to the k e to the negative k times negative k plus k x to the k minus 1 e to the negative k. And that's going to be x to the k minus 1 times, I should pull a k out as well, times 1 minus x over e to the k. Okay, and that, for x being positive, this is negative here, positive, positive there. So that's less than 0 for x being greater than 1. Okay, so we take the integral from 1 to infinity of x to the k e to the negative k dx. That's the limit as b goes to infinity. Integral from 1 to b of x to the k e to the negative k dx. So, improper integral. And this works out to be the limit as b goes to infinity of negative x to the k e to the negative x plus integral 1 to b of x to the k minus 1 e to the negative x dx. And continue this process, we get the limit as b goes to infinity of negative x to the k e to the negative x plus kx to the k minus 1 e to the negative x plus k minus 1 integral from 1 to b of x to the k minus 2 e to the negative x dx. What this works out to be is the limit as b goes to infinity of negative x to the k e to the negative k. And I'm using a formula from the tables. Plus k x to the k minus 1 e to the negative x plus k times k minus 1 x to the k minus 2 e to the negative x plus you'll have a k times k minus 1 times k minus 2 times times 2 times 1 x to the 1 e to the negative x plus k times k minus 1 k minus 2 times 2 times 1. There's no 1 here. The 1 is up here. Just e to the negative x. I should say x to the 0 e to the negative x. From 1 to b. Now, in every case, when we plug in the b for these powers, it's going to go to infinity down below quicker than above. And that's a whole L'Hopital's rule thing. We did some problems like that. We did L'Hopital's in 8.7. So that's when we plug in the b. So everything with the b, every time with the b in is going to go to 0. So our limit as b goes to infinity, that's going to be negative b to the k over e to the b plus k times b to the k minus 1 over e to the b plus k times k minus 1 x to the b. This should be x to the b minus 2. No, b to the k minus 2 over e to the b plus k times k minus 1 times k minus 2 times 2 x to the 1 over e to the b, that should be b to the 1, plus, and then you have your k times k minus 1 times k minus 2, all the way down to 2 times 1. That's over e to the b. So each of these, for the b part, are going to go to 0 because of the infinity. You have infinity to a power over e to the infinity. Those all go to 0, and that's a L'Hopital's rule thing we saw before. So these are all 0. Then minus, put 1 in for all the x's. Negative 1 to the k, e to the negative 1, or just do over e. Then we have k times 1 to the k minus 1 over e, plus k times k minus 1, 1 to the k minus 2 over e, plus k times k minus 1 times k minus 2, 1 to the k minus 3 over e, plus, and you're going to be down to k times k minus 1 times k minus 2 times 2 over e, plus k times k minus 1, k minus 2, 2 times 1 over e. And that's a fixed value. The rest of this will all be a fixed value. So, the sum as n goes from 1 to infinity of n to the k, e to the negative n, converges. It's not pretty, by any means. Not pretty. Really could use like the whole page for this one. But the point to it is, these all go to 0 because you have infinity to a power over e to the infinity. And we saw before, we did that with L'Hopital's rule, that would go to 0. You can keep taking the derivative. The numerator goes away to a constant. The denominator does not. You're always going to have the e to a power. All these would represent a fixed value. It's a messy problem. You're probably not going to deal with k being a million. K might be 3, might be 5. But I did a lot of expanding here. So that's fixed value. So it converges. Okay. A couple things if you can read through here. P series, the sum n goes from 1 to infinity of 1 over n to the p is 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, where p is a positive constant. That's a p series. Just recognize that as a p series. Harmonic series, the sum as n goes from 1 to infinity of 1 over n. So the harmonic series is one of the p series where p is 1. That's 1 plus 1/2 plus 1/3 and so on. That is divergent. Okay, computer fell asleep. Screensaver went on, didn't go to sleep. That is, no, sorry, not convergent. That is a divergent series, as I said in, I think it was 9.1 we talked about that. No, it was 9.2. This is a divergent series. A little counterintuitive because we think that would converge. So I'm going to go ahead and scroll it on. So you've got to pause now if you want to keep that, or pause and watch that, or you're going to have to rewind. Okay. Theorem 9.11 or 911, convergence of a p series. The p series, as we saw earlier, it converges if p is bigger than 1, diverges if p is between 0 and 1, inclusive of the 1. So use theorem 9.11 to determine the convergence or divergence of the p series. Okay, so what we have here is the sum as n goes from 1 to infinity of 1 over n to the 1/5 power. Well, 1/5 is less than or equal to 1, bigger than 0. So this diverges by the p series. by theorem 9.11. That was a lot less work than the previous problem. Okay. Last example from this section. Find the positive values of p for which the series converges. So, if p equals 1, this diverges. Because the power on n is 1. So let's look at the integral test. If we have the integral from 2, notice it starts at 2. So from 2 to infinity of 1 over x natural log of x to the p power dx. That will be the limit as b goes to infinity, integral from 2 to b, 1 over x natural log of x to the p. So we'll have the limit as b goes to infinity, integral from 2 to b of natural log of x to the negative p times 1 over x dx. So if I did a u substitution, I don't know that we really need to do the u substitution, but if we say u is natural log of x, its derivative is 1 over x dx. So we can integrate this. If we integrate this, we'll get this, add 1 to this power p. So this becomes the limit as b goes to infinity of the natural log of x to the power of negative p plus 1 over negative p plus 1. You could also think of that as 1 minus p from b to 2. No, 2 to b, excuse me. Okay. So we have the limit as b goes to infinity of natural log of b to the negative p plus 1 over negative p plus 1 minus natural log of 2 to the negative p plus 1 over negative p plus 1. That would be natural log of infinity to the negative p plus 1 over negative p plus 1 minus natural log of 2 to negative p plus 1 over negative p plus 1. So, if this power, if the overall power is negative, this natural log of infinity goes down below. So negative p plus 1, if it's less than 0, we have negative p is less than negative 1, and divided by negative 1, p is greater than 1. So if p is greater than negative 1, or greater than 1, the series converges because it puts the natural log of infinity in the denominator. And that's it. And we'll stop there. Okay, that's 9.3. Shorter section. We had some long problems though. Okay. Let me know if you have any questions, and I will see you guys online.